and what actually makes it work, right? So we know at a conceptual level how CNN works and how it is actually able to detect and detect objects from an image. So that is the so we'll be looking at the code and in Python, how are we actually implementing the CNN architecture, right? So that's the first thing we'll be looking at, and the second thing is we'll be briefly touching what is reinforcement learning. Okay, reinforcement learning is a second type of deep neural network. So the first one we saw was convolution neural network. The second one is the reinforcement learning. So we'll do that once we're done with this code flow. Okay, so let's get started. So if you see, this is the same architecture what we are following, what we have seen in the previous session. We have an input layer, we have a convolution layer, and then we have a pooling layer. Then we have, so the non-linearity or the ReLU, the rectified linear unit, what we saw, right, was will be part of the convolution layer 1 only. So we do not show it as a separate layer. Okay, so convolution layer 1, pooling layer 1, and this again, these can be actually repeated to have a more deeper network in the sense if you have multiple features, right? So this convolution layer 1 will be able to extract the lower level features as we saw, right? And then the convolution layer 2 will extract some higher level features. So if your image or if your image is very complicated, if it has multiple hierarchy of features, then what you should be ideally doing is you should be using a convolution network which is having multiple networks, multiple deep layers, right? But then one thing to note here is you might ask a question, to what extent can we actually copy, we can increase the number of layers in a deep neural network. So it actually doesn't mean that you keep on increasing, you keep on adding the hidden layers and the performance increases. That's not the case. In fact, in general case, what we do not cross more than 2, 3, 4 layers of the deep neural network, because after that there are not much features to be extracted. So whatever the hidden layers you are adding after the fourth hidden layer, for example, it doesn't add any value to it, right? So I hope I'm clear on that front. So let's get started. So I think on day 2 you were exposed to the MNIST dataset. MNIST dataset is the handwritten dataset, right? So which has the digits from 0 to 9. So we'll be working on the same dataset, and the goal is to implement the convolution neural network architecture to solve the problem of object handwritten digit recognition, right? So the most important thing is called the TensorFlow here, because TensorFlow is a framework which you have to import, which is actually providing the support for convolution neural network. So only with the help of this TensorFlow framework we'll be able to implement the convolution neural network and its various pooling layers and the fully connected layers, right? So this is the most important thing of TensorFlow. Probably you can Google more about TensorFlow. In fact, TensorFlow is developed by Google itself for the end users to create their own deep learning model using the CNN. So do you see this pip install TensorFlow equal to 1.2? What is actually doing is, in this Google Colab platform, it is installing the TensorFlow framework, and this equal to 1.2 is where I have mentioned the specific version of TensorFlow. If you do not want to work with a specific version, you just don't give this equal to 1.2, right? So that is the reason I want to specifically work with 1.2 version. So I have given that. So you see, this is the entire process where it actually installs the package of TensorFlow in your Google Colab working platform. After that, we are going to be importing the MNIST dataset. Okay. Now the way how we do it is from TensorFlow, which we have imported over, which we have installed over here, right? From TensorFlow, we are going to be importing the MNIST dataset, and then we are going to be reading the dataset and putting into an MNIST, you can say a Python list. So this is one hot encoded. So we also, what is one hot encoded, right? Whenever we have a dataset which is categorical in form and we need to convert it into a numerical, so we have the one hot encoding, and that is how the MNIST. So now this MNIST variable is going to hold the dataset, the entire handwritten dataset. And then we have the numpy array is where we are going to be, so we are working with images, right? Now if you see, images is nothing but set of pixels, right? And we will be treating, or we will be working on the image as a set of an array, basically a 1D array. And that numpy is nothing but it is a Python support for you to be able to work on a array. So it is called a Python numpy array. And then we have this pie plot for plotting the images what we wish to visualize, right? And these are few hyperparameters. So what are hyperparameters exactly? So whenever we are working with machine learning or deep learning models, there are few things we can control from our side. So one is the learning rate. The learning rate actually tells how quickly you should learn, or how quickly the model should learn, right? Now there's a catch here. If the learning rate is too high, what happens? The model might learn too quickly, but it might not learn too properly, right? So the entire training process might be wrapped up quickly, but then the learning might not have been done in a proper manner. So it's like doing a task, like your mom might ask you to do a task, you might do it quickly, but you might not do it properly, right? So that is the learning rate being very high. And if the learning rate is too small, then your entire training process might take a long time. Though you might achieve a desirable output, but then it might take a long time. So coming up with the apt learning rate is a tact in itself, right? So learning rate, I have put it as 0.001. Number of steps is the number of iterations. So we saw in the training phase, the deep learning model never learns in the first step itself. It has to undergo multiple steps, right, to be able to understand and back propagate and assign the weights properly, and then finally be able to learn how to classify. So the number of steps we have given is 500 for it to be able to learn properly. And batch size. Now again, this is another concept where we the input images whatever we have, we do not give it all the input images at a go in the machine learning in the deep learning model. Rather, what we do, we give it in set of batches. So the batch size is 128. That means one batch will have 128 images, and those 128 images will be given to the training model. It will run for 500 steps with a learning rate of 0.001. Then we will give the second batch, third batch, and so on. Okay, the batch size is because we don't want to overload the network with all the images at once, right? And number of inputs. So if you see, every image will be one input to the model. Okay, and if the model the image dimension what we're using is basically 28 cross 28, and it is generally denoted as 28 cross 28 cross 1. That one actually denotes what is the number of channels, or what is the RGB value of the image. Since we are going to be using a black and white image, the channel will be 1. If you are using a color image, the channel will be 3, basically RGB, right? So in that case, if we are using a color image, the input dimension would be 28 cross 28 cross 3. So now for if we're sticking to size, yeah, size only, then 28 cross 28 is the image size. Then the input to the your network will be 784. That is nothing but 28 cross 28, because like I told you, right, your image is nothing but a matrix, right? 28 cross 28. When you're going to give it as an input to the network, you will stack it into an array, right? So you're going to have 784 pixels in the single array, right? So this is, so you're going to have 788 pixels over here in the input layer. Now coming to the class, the number of classes is 10 because we have a handwritten digit data set, right? So we have 0, 1, 2 all the way to 9. So there are 0 to 9 possibilities of classes, right? Dropout. The concept you might not need to learn now very in depth, but what it basically does is, you don't want the model, or see, basically we're talking about deep learning, right? We don't want to talk about deep memorization. So whenever a human is learning something, what happens, where whatever he has learned, he should be able to do that, and whatever he has not seen, like the questions we go and see in the exams, right? We might have to apply our concepts to get the solutions to the questions, right? In the exam, whatever we see, we are not often thrown the same question, right? We might have to apply our mind, apply our learnings, and solve a different question, right? So there's a difference. So I hope I'm making a clear difference between memorization and learning, right? So what happens when your model has perfect learning on your training data set, perfect learning, there's a possibility that when there is a test image which is slightly different from what your training image was, it might not do well, right? Because the model has only learned on training data set, and you give anything different, the model cannot predict. That the problem is called overfitting. The problem of overfitting is basically the model has only learned the training data set properly. So this is a case of memorization. So what we do, there is a process of called regularization, where we ensure that the learning process, or you can say the memorization process during the training is reduced. So what happens, even any new sample comes in the test sample, which is slightly different from the training sample, the model should be able to classify that correctly. Okay, so this dropout actually says that there are few outputs. So I'll have many output neurons over here from pooling layer 1 or pooling layer 2. Dropout basically says you just drop out the output of one of the few neurons. So that should not matter. You get it, right? So if at this point of time we have 5 neurons after this pooling layer 1, right? We have 5 neurons after this pooling layer 1. Each one of them is giving an output, right? So we do not want a memorization. We do not want the model to train 100% or perfectly fine on the training data set. So what we do, out of these 5 neurons, 1 neuron we just drop the output. It gets lost. We don't want that output to be perfect. Okay, so that is what dropout is actually saying, that I do not want a memorization. Let it not be a perfect learning on the training data set. So this is what it says. 0.25 is the probability that I'll be dropping the output of a particular neuron. Now coming to the convolution network, so here we are defining a convolution network function where yeah, so there's a reshape. So number one, see, TF is basically TensorFlow. So whatever function we are using, right, the tf.layers.conv2d, this TF is the TensorFlow what we imported over here. One second, yeah, import TensorFlow as TF. So whatever libraries or whatever routines we are using is because we have installed this TensorFlow in the beginning itself, right? So now coming to the first process is of reshaping the tensor, or you can say reshaping the image. Okay, and one second. So here X will be your input, which is nothing but an array of pixels, which is nothing but the image, right? I'll be reshaping it. Now what do I mean by reshaping it is, initially it'll have 28 cross 28, that is the size, and we saw it, since it's a black and white image, the channel will be 1. Okay, and the batch size, initially the batch size, it will not have any batch size, because I'm resizing, I don't need a batch size. So then after the thing is reshaped, then we have a convolution layer. Now remember I spoke about filters. There are filters in the convolution layers which are actually responsible for extracting certain features from the image, right? So the feature extraction part happens in the convolution layer. So now conv1 is basically the convolution layer 1, where I'm calling tf.layers.conv2d. It's a convolution 2D, right? We're working with images matrix, so it's a 2D, and X is the input, which is which I told you is an image basically. 32 is the number of filters we want to use in convolution layer 1, right? And 5 is basically the kernel size, the 5 cross 5. We saw the convolution, we were using a small matrix to do on a bigger matrix, right? The bigger matrix is basically the image. 32 is the 32 different features we want to extract. So we'll have 32 different filters, and each filter will have a size 5 cross 5. So remember, always the kernel will be a square matrix. So whenever you're giving 5, basically means 5 cross 5, right? And the activation function, as I told you, will be using ReLU, which basically says any negative value you convert it to 0, right? After this, for whatever output you got over here, conv1d, that output you give as an input to the max pooling layer. So tf.layers.maxpooling2d will actually call the max pooling, right? What it does, it has a kernel of size 2. So 1, 2, 3, 4. It has a kernel of size 2, and stride also 2. So remember what I told you about the stride. It is actually by how much do you shift the kernel. Okay, and then finally the output what we get after the convolution layer and the non-linearity layer and the pooling layer is actually stored in convolution 1. Okay, now remember what I told you, the output of this can actually be repeated, right, multiple times. So this entire pair of convolution and pooling can be done multiple times to create deeper networks, right? This is exactly what we're doing over here, where we have a convolution 2D. Okay, this convolution 2D is going to be taking the input of convolution 1, okay, this one, and then it's going to be performing the same convolution 2D with an activation ReLU. Again, it will going to do max pooling, and again you're going to have convolution 2D. So here we have two hidden layers basically. That's what you can understand, right? And then finally, once this so we have implemented convolution 1 and convolution 2. After that, we'll be implementing the fully connected layers. The fully connected layers, like I told you, is where the class voting happens. For each class 0 to 9, it will give the probability. What is the probability for that class getting predicted? So now coming to that, so this is how you actually convert. So if you remember in the 1 second, so we had this output in the fully connected layer, which we actually made it into a single array, right? So this was actually made it into a single array, then this and this. So the entire thing is called the flattening process. These images are actually flattened. So that is what you mean by the flattening over here. 1 second. Yeah. So fully connected layer first has to flatten the output what is given by conv2. Okay. Once it has flattened, I get a single dimensional array, and after that I apply this layer dot dense fc1 1024. So this actually gets me the fully connected layer. And what this 1024 actually means is I am going to be having 1024 neurons in that fully connected layer. I can define how many neurons I want. And finally, the output what you're going to get will be a function of your fully connected layer and the number of classes. So this is where the class voting actually happens for each class. And then I have to give return the prediction value. Okay. So these are some environment values which I'll not be touching much. So the concept of the convolution, the entire convolution neural network is actually covered in this create the neural network module. I hope you people have got the code, right? So you can understand that. Here there are these few environment values which are being set, and there is something called as Adam optimizer, and so optimizer concept I just want to probably tell a few lines. So what optimizer does is we have seen in the neural network there's the process of backpropagation, right? So what we saw, that neural network in the first iteration, it does not give you the right answer in the training process. Then it actually has to go through multiple process, right? So what happens in each process, if there's a wrong classification, the network actually goes and changes the values of the weights until you get the correct answer. So that process, the entire process is called the backpropagation process, right? And that backpropagation process, what it does, the aim of the process is to reduce the error, right? Let me just show you here, just so that you connect well. Yeah. So you see, this is the case I took in the morning session as well. In the first iteration, it has not classified perfectly right? So there is some error. There is an error of 2. After that, subsequently, it does, it finally gets an error 0. So this entire process is called the backpropagation, whose motivation or whose objective is to reduce the error. So that is what this optimizer function does. And Adam optimizer is one such type of optimizer. So the optimizer role is to minimize the error in the backpropagation, which is in the learning process, right? So we have done that, and finally, what happens is we have actually using the TensorFlow estimator, the entire model and the function is actually set. So now we can go ahead and run the model. Model is whatever we have actually created over here using the conv1, conv2 fully connected layer, right? And so while running, we have to ensure what is the batch size, what is the number of epochs. So you remember we have given the batch size is 128, number of epochs, probably say epochs is basically how many times the same sample should be trained again and again, right? So once we have given these are these hyperparameters. So as a user, you can change these values according to your application and your needs. And you call this model.train inbuilt function. and this is the input function, and this is the input function is again defined as the TensorFlow's inbuilt input function, which is going to be giving whatever input you have, right? Whatever input I got out of this last TensorFlow fully connected layer, and once that is done, 1 second. Yeah, so you not here. Yeah, and you give the number of steps. So the number of steps is actually how many times the learning should happen. So in this particular case, the number of steps were 3, right? So if you have a bigger number of steps, then you can be rest assured that the training is going to be fine. And then once I'm done with training, this is what happens after training. So the model is trained, right? Now once the model is trained, we want to understand how good the model is. Any machine learning model or deep learning model, we have to have a metric to say how good that model is, and that is done by accuracy, right? Accuracy and the loss function. So when we do a model dot evaluate, we get an accuracy, training accuracy of 0.98, that is 98%, and we get a loss of 0.04, that is also great, 4%. So considering the model is built, this is how we can actually test the correctness or the performance of the model. Now let's test how good the model is on test data set. Now what do I mean by test data set? These are the samples which was not used to train the model with. So these are new samples, right? So when we see this is the 7 and the model prediction is 7. This is 2 and the model prediction is 2. This is 1 and the model prediction is 1 and 0 and so forth. Right. So the demo is done for convolutional neural network. Let me quickly go to reinforcement learning. I'll just briefly touch upon what reinforcement learning is. So convolutional neural network was good, especially for a task which required object identification. Right. Whenever I have image processing, image recognition, and video recognition task, then CNN is the best tool out there in the market. But now what happens if we want to develop some sort of a AI robo which can play games and do certain tasks, right? We want it to do something. We don't want just detection or no object detection or a face recognition. In fact, we want it to do something, play a game, for example, play a chess, right? We have seen now the AI is so developed that AI robots can actually defeat the best player in the chess, right? So these are done by a network called reinforcement learning. So reinforcement learning is another type of deep learning model, so which is actually different from CNN. I'll tell you how. It in fact is very different. So what is learning? Learning actually takes place as a result of interaction between an agent and the world. And so how does a baby learn? So if you see the baby learns to walk, for example, it initially does some steps, and then it.
Hello? Shivaselvan, sorry for the interruption. Right?
Mm-hmm.
2-3 minutes, can you wind up, right? Because I think they are kindly wind up the session and share the testing. Yeah, they are, their minds is on the assessment here, okay? Right?
Okay.
I will share, sorry for the interruption, don't mistake. Right?
Sure, sir,
this is the classical curse of the last day speakers, the workshop, okay? Right?
No issue.
Right, so I've already pinged your email IDs in the chat, right? So they can get in touch, and we will share the PPT, the notebooks, and all, right? Thank you, Ishan. It may be what are winding remarks you want to make. You make 3 o'clock. We'll start.
Okay. 3 minutes. I'll just wind it up in 3 minutes. So if you see a baby, how does it learn? Is I actually does something and it fails, right? And when it fails, it knows, okay, whatever it did so far, it should not be done again. And when it somehow learns to walk partially, it knows, okay, this is the way I keep my balance and this is the way I do my things, so I should do those things more often. So this is learning, actually learning from the environment. So there are types of learning. One is the supervised learning. That is what we saw in the classification and the CNN process, where we had a training phase where we gave a training data. But when you do not have a training data, for example, a baby is learning to walk, the baby does not have a training data. So how does it learn? It learns due to reinforcement learning, where the baby or the agent in this case is acting with the environment, and it receives some sort of a response. And if the response is positive, like if it is able to walk, then whatever it did to walk, it promotes that activity. And whatever whatever activities led to it falling down, it will not do that activity, right? It's pretty simple. So let me just so you people have this PDF. So any doubts you can always ping back to us. So there's this very famous example where RL is used, that is the Pong game. So you see here the ball is actually moving, and then the one, I think one end is actually handled by the system, the another end is handled by the user, where he has to push the ball, right? The ball should not go here, so the board should not be missing the ball. So this is a classical example of a reinforcement learning, where the machine is learning how to play a game against a human, right? And the most important part, or how does it learn, let me summarize it quickly since we're running short of time, is when the basic idea behind the entire reinforcement learning is when this board, right, when it can hit the ball, suppose it goes up and hits the ball. So what it sees, that I have gone up and I have hit the ball, then there's a reward. There's a reward of +1. So what it does, it follows that process more. Second case, say the board actually went down and missed the ball. It could not hit the ball. So there's a reward of -1. So now the machine knows that I should not go down, rather I should only go up. So this is the entire process of reinforcement learning. Reinforcement learning is a session in itself, but since the slides are shared with you, do go through the slides, and it will take time to wind. Hello. Can you?
Somebody is muted, நினைக்கிறேன். Unmuted. Link is shared here. Masa, you can put the link again.
Okay, sir.
Okay, and closing it in another 1 minute or so. So reinforcement learning applications, right? So where we have robotics for industrial automation, we see the cars, the vehicles, and so many things are automated. The manufacturing process is automated, right? So how do you think the robot is actually learning what to do? So that is all because of reinforcement learning. And then machine learning, data processing, aircraft control, and some of the few applications to name a few. And then I think Garg sir had actually asked me what are the various types and applications of deep learning models. That was a great point, because you would want to see a summarized result of what are the different types, right? And what are the applications. So you could go out of your interest and Google more on that. So this last slide I have added after that session, which actually says, hello. Yeah. So yeah, I hope this is clear, and I would just like to end it there. Yeah. Thank you all.
Thank you. This is a typical J.
Yeah, thank you very much, sir.